All right, similar example to the previous one. The difference is when these vectors are arranged, they're forming a non-right angle triangle. So for the example, we want to take u and v and w, and they're as shown. Determine an expression for w. So we want to get w equals as a linear combination of vectors u and v. Given that, we know the magnitude of u is 1, v is 5, and w is 8. So if we want this to work, it actually can't work as is because the u vector had to be stretched a little bit, so it's been multiplied by an a value. The v vector has to be multiplied by some other value as well in order to get it to work to be this w vector. So we know the magnitudes. So on the previous one, it created a right angle triangle. This one's a non-right triangle. We know all three angles, and we know a side. That means we can use sine law. So using sine law, sine A over A, sine B over B, sine C over C, we find the process is very, very similar, and you can label the sides however. I'm going to use, this is side A, seems to match up a little bit nicer that way. So sine A, so we would have sine of 40 over A, magnitude of u, which is 1. I'll put 1 in there. Sine B, so we'd have sine of 20 over B multiplied by the magnitude of V, would be 5, and sine of 120. Magnitude of the W vector is 8. So that proportional relationship will break into two equations for us. So I end up with sine 40 over A equals sine 120 over 8. I end up with sine 20 over 5b equals sine 120 over 8. Isolating and solving, a would equal 8 sine 40 divided by sine 120. So there's one coefficient or scalar value. And the other one, b would equal 8 sine 20 over 5 sine 120. There's our other coefficient. So there we are. So that means that our w vector is equal to 8 sine 40 over sine 120. So that's the that's the scalar value that's multiplying the u vector plus 8 sine 20 over 5 sine 120. That's your v vector. So there you go. There's the final answer right there. So if it's right angle triangle, use the SOHCAHTOA. If it's a non-right triangle, then you either have to use sine law or cosine law. So hopefully it's sine law. All right. And final example here. So now I'm not given a diagram. I'm given an algebraic expression, or I'm given the coordinate form of the vectors. And what I want to do is I want to write w in terms of u and v. So that means that the w vector is going to equal au plus bv, which means that a, and I know the value of the u vector, that's 6, 2, and 9, plus b, and I know the v vector is negative 4, negative 7, 1. And with this one, I actually know what the w vector is. So 15, 22, 1.5. So what does this then tell me with it in coordinate form or the algebraic format here? I know that my x components, so underneath here from this, I know that my x components have to equal 15, and you get 6a minus 4b. I know that the y component has to be 22, and that comes from 2a minus 7b. And finally, 1.5 is equal to 9a plus b. Still, we have three equations, two unknowns. So we need to solve for a and b in this case. Doesn't matter which one you take, which two equations. So what I'm going to do, I'm going to take the first two equations, and I'm going to leave the first one alone. So this goes back to why we learned how to do substitution elimination in grade 10. I'm going to multiply that second equation by 3 to get the a's to match up. So that means I have 66 equals 6a minus 21b. Doing our subtraction here, we would end up with 0a and negative, oops. So that's going to be adding, and we're going to take that away. So we'd end up with 17b. And on the other side, 151, so negative 51. And everyone knows that 51 divides evenly. So therefore, b equals negative 3. Remember, you have to use one of the two equations from above. So, kind of working sideways in this case. So therefore, let b equal negative 3. So 15 equals 6a minus 4b. 15 equals 6a minus 4 times negative 3. Please make sure you use one of those original two equations. You can't use the third equation at this point. Subtract 12 from both sides, and I get 3 equals 6a, or a equals 1/2. Now, this has to work for all components. So you still have a third equation. There's that z component we have to check. This is the a and b value that will work for the first two equations, so your x component and your y component. The question is, will it work for the z? So you must check third equation. So it doesn't matter which two you pick to start with, you have to check the third equation. So left side, right side proof. Left side's 1.5. Right side, 9a plus b. So 9 times a half minus 3. So 9 times a half is 4.5. Take away 3, 1.5. Therefore, left side equals right side. So final answer, w vector is equal to 1/2 the u vector minus 3 times the v vector. There you go. Now the question is, what happens if this wasn't true? So what if ls is not equal to rs? So here's the thought bubble. If ls isn't equal to rs, that would mean that w cannot be written as a combination. And I'm getting a little bit ahead of myself in this case, because that's looking at the next unit. Therefore, u, v, and w are not, are independent. Independent. And you're asking yourself, what's independent? Well, let me tell you, you need to tune into the next lesson, because the next lesson is independent and dependent vectors. So, okay, there's the assigned homework. Like I said, going through the note, doing the homework, you should be able to write and determine coefficients for linear combinations. So, good luck with that. If you have any questions, please feel free to ask.